Greetings to our lecturer Dr. Noraini Ahmad and my fellow classmates. My name is Tan Kayi and my group members are Muhammad Shahmi, Roy, Adam Daniel, Muhammad Zarfan, Muhammad Firas Iman, Shafiq Azim and Luqman Amirul Hakim. We will be presenting about solar energy conversion, photoelectrochemical cells. Without further delay, let us begin.
What is solar energy conversion? Solar energy conversion is a process of transforming sunlight into usable energy, such as electricity or chemical fuels. This can be done by photovoltaic cell (PV), light to electricity, or photochemical cell (PEC), light to chemical energy. Why is electrochemistry important in solar energy conversion? First, energy storage. Solar panel only produce electricity when the sun is shining. So extra energy must be stored to use at night or during cloudy weather. Electrochemistry made this possible by storing solar energy in batteries and supercapacitors. Batteries keep energy through chemical reaction, while supercapacitors store charge on their surface for faster release. With this stable and reliable supply of solar power can be obtained through batteries and supercapacitors. Second, electrolysis for chemical production. Electrochemistry made it possible to use solar and electricity to split water or convert CO2 into valuable chemical. This offers a path to a sustainable fuel and chemical production using sunlight instead of fossil fuel. Electrons from solar energy react with CO2 molecule and break the strong CO bonds. Then the atom rearrange to form a new useful chemical compound. For example, formic acid HCOH used in batteries, methane CH4, renewable natural gas, ethylene C2H4 for plastic production. Last but not least, material synthesis and optimization. Material synthesis and optimization play an important role in solar energy conversion. This process uses low-cost and low-energy methods such as electron deposition, which help reduce overall production expenses. With this technique, researchers can adjust material composition and structure with high accuracy. This makes it easier to improve the efficiency of solar devices.
What is a photoelectrochemical cell? A photoelectrochemical cell is a device that generates photocurrent and consists of an electrolyte and a photoactive semiconductor electrode. When the semiconductor electrolyte interface is illuminated with light, whose energy exceeds the semiconductor's bandgap, electron hole pairs are produced. The charge distribution in the oxide-based semiconductors forms a space charge region, which facilitates the separation of these electron hole pairs. Here, you can also look at the basic structure of photoelectrochemical cells.
I will explain the basic mechanism of how a photoelectrochemical cell works. First, when light hits the photoelectrode, the photons are absorbed and excite the electron to the higher energy level. This is called the light absorption mechanism. Next, once the electrons are excited, charge separation can occur. The molecules split into hydrogen and oxygen. The electron move toward the cathode while the holes move toward the anode. This creates the two separate pathways for redox reaction to happen. The cathode, hydrogen ion gain electron and are reduced to form hydrogen gas. At the anode, water molecules are oxidized to produce oxygen gas. So we have reduction happening on the right and oxidation happening on the left. As the result, for overall outcomes, the light energy converted into the chemical energy. This chemical energy is usually stored in the form of hydrogen gas, which can be used later as a clean fuel.
I will be explaining the materials of a photoelectrochemical cell. For short, it is called PEC. PEC consists of three main components, that is the working electrode, in this case it is photoanode, a counter electrode and an electrolyte. Common materials for a photoanode include titanium dioxide, which is highly stable, non-toxic and low cost. Next is hematite. Hematite is more cost saving and also non-toxic. And lastly, tungsten trioxide, that is very stable in acidic solutions. Furthermore, Common materials for contour electrodes include platinum and carbon materials such as graphene and carbon nanotubes. Platinum is a good material to be used as it is highly effective due to its excellent electrocatalytic activity. However, a downside is that platinum is expensive. Second, these carbon materials are commonly used as they are cheaper. Most carbon materials are also abundant in types, making it a good alternative. Last but not least, a common material for an electrolyte is aqueous electrolytes. Aqueous electrolytes are solutions that contains acid, base, or salts which function as ion movement facilitators. I will now pass to my friends to explain the real-world application of photoelectrochemical cells.
So for real world application of photoelectrochemical cell, these are the common application that we can see in today's world. The first one is the PEC water splitting, the second one is PEC CO2 reduction, and the third one is the PEC pollutant degradation. So we will talk more detail about this application. For photoelectrochemical cells, water splitting. PEC water splitting process is one of the electrical cells in electrochemical chemistry. This process is an environmentally friendly and sustainable method. PEC will convert light energy into chemical energy. This energy is then used to drive the reaction to produce the required product, which is hydrogen. The hydrogen gas produced will provide many benefits to technology and human use. So, how do photoelectrochemical water splitting works? So the first thing happen is the semiconducting electron will absorb photon and create electron-hole pairs. So the light energy absorbed is used by the electron at n-type photoanode to excite to the conjunction band and leave holes in the valence band. The electron is then moved from photoanode to the photocathode. The electron reduces the hydrogen ion to the hydrogen gas. Then the holes at valence band will stay at photoanode and oxidize the water into oxygen. At p-type photocathode, the light energy is also absorbed by the electron and excited to the conjunction band. The electron will stay at the photocathode and reduce the hydrogen ion to hydrogen gas. The holes at the valence band will remain in the photocathode to neutralize the incoming electron so that both electrodes are balanced. What are the material used in semiconductor? So first, for photoanode, type of material used is like titanium dioxide, hematite, tungsten trioxide, and bismuth vanadate because these are the material that are able to generate holes that can oxidize water to oxygen gas. And for photocathode, the type of material used are like gallium phosphide, gallium indium phosphide, silicon, cuprum oxide because these materials are able to generate electrons that can reduce water to hydrogen gas. In real-world use of PEC water splitting, the main purpose of PEC water splitting is to produce hydrogen that can be used first in transportation. For the conventional internal combustion engine and battery electric vehicles, hydrogen fuels can provide a better alternative to it. This will offer zero emission of greenhouse gases, fast refueling, and long driving distances. In fuel cell vehicles, hydrogen stored in the tank react electrochemically with oxygen to produce electricity, which then powers the electric motor that drives the vehicle. The second one is the ammonia production. Most of the fertilizer and chemical products out there use ammonia as the main component in it. Through the Haber-Bosch process, ammonia can produce from natural gas, but the consequences is this method will produce a huge amount of carbon dioxide. Using renewable hydrogen, we will be able to provide a cleaner pathway, allowing ammonia to be produced without generating carbon emission.
So for my part, I will be explaining photoelectrochemical or PEC carbon dioxide reduction. Photoelectrochemical carbon dioxide reduction is a solar-powered process where carbon dioxide and water are converted into useful fuels using semiconductor electrodes. Many studies describe it as a form of artificial photosynthesis because the system directly uses sunlight to drive the chemical reactions. Here is how the mechanism works. When sunlight hits the semiconductor, its electrons become excited. These excited electrons move to the photocathode when they reduce carbon dioxide into products such as carbon monoxide, methane, methanol, or formic acid. At the same time, the positive charge or holes travel to the anode and oxidize water into oxygen. Because the energy mainly comes from sunlight, the system requires very little external electricity. which is one of the key advantages highlighted in photoelectrochemical research. For the materials, one example used in current studies is a photocathode made from cuprous oxide combined with gallium oxide and titanium dioxide. Cuprous oxide absorbs sunlight and performs the carbon dioxide reduction step, while gallium oxide and titanium dioxide help form a stable p-n junction that improve charge separation and increase durability. A catalyst such as tin or tin oxide is usually added on the surface to enhance efficiency and improve the selectivity of carbon dioxide reduction. This technology is important because it converts carbon dioxide into carbon neutral fuels, which lower greenhouse gas emissions and store solar energy in the form of chemical energy. In overall, photoelectrochemical carbon dioxide reduction is a promising pathway for clean and sustainable fuel reduction.
Alright, so this slide is about photoelectrochemical or PEC, pollutant degradation. Basically, it's a technique that combines light and electricity to break down harmful pollutants in wastewater. You can think of it as an upgraded version of photocatalysis, but it is faster, cleaner, and more efficient. Let me walk you through how it works. Firstly, when light hits a semiconductor material, it creates two important things, which is electron, the negative charge, and holes, the positive charge. These holes are very reactive and they are the key players in this process. Then, when we apply a small voltage, it helps separate those electrons and holes even better so they don't recombine and become useless. Now, the interesting part happens next. These holes react with water to form hydroxyl radicals, and hydroxyl radicals are incredibly strong oxidizers, so they can break down almost any organic pollutant. Finally, these radicals attack the pollutant molecules and break them into much smaller, harmless byproducts like carbon dioxide and water. So in the end, the contaminants are completely degraded. So, why is PEC effective? It works very well with sunlight. It's faster than normal photocatalysis because of the added electrical boost, and it doesn't require a lot of chemicals, which making it more environmentally friendly. And for the materials, the common ones are titanium dioxide, which performs really well under UV lights. And the second is hematite, which is cheap and abundant, and zinc oxide, which also has strong photocatalytic properties. So overall, PEC is a powerful method because it uses renewable energy sources, which is light and small voltage, to clean out wastewater efficiently.
Advantages of photoelectrochemical cell. Solar to fuel conversion. No need for external electricity. PEC use sunlight as their main source of energy, so they do not need electricity from the power grid. This means PEC system can work without using fossil fuel or any outside supply of electricity. This makes PEC technology cleaner and easier to use in many different places. Make clean energy from sunlight. PEC turns sunlight directly into chemical energy such as hydrogen. This direct conversion helps save energy and make the system more efficient. It also reduces air pollution because the system produces energy without burning any fuel. Scalable for different energy needs. PEC system can be designed in different sizes to meet energy demand. Small unit can power home or remote areas, while larger system produce hydrogen for industry. This flexibility makes solar to fuel conversion suitable for both local and large-scale application. Environmental benefit: reduce gas emission. PEC produce hydrogen and other fuel without emitting CO2. This can reduce carbon emission by up to 100% during operation if powered purely by sunlight. It made the fuel much safer for the environment. Low environmental impact materials. PEC materials are common and non-toxic such as titanium dioxide or iron oxide. It ensures the system is suitable from when the parts are first made until its components are ready for recycling. Support clean energy system. PEC system work well with renewable energy and help create a fully green energy cycle. Sunlight to hydrogen to electricity, making our energy is much more effectively. Storing the energy as hydrogen is crucial because it solves the challenge of constant supply, allowing clean power to be used day and night. Cost benefit: lower operational cost. Once installed, PEC system use free sunlight as its only power source. It is crucial because the main job is hydrogen production, which typically need huge amount of electricity. Since PEC do not need external power, they completely remove the major energy cost. This will reduce operational expenses. Use of low-cost material. PEC cells are built using cheap and widely available material like iron oxide and carbon-based semiconductor. This helping to lowering overall manufacturing cost by 30 to 50% compared to rare metal for base system. Long-term economic efficiency. The production of solar fuel through PEC can become cost competitive as technology improve. With fewer moving parts and minimal maintenance, PEC systems have the potential to reduce long-term energy costs for industry and consumer.
Here are the challenges of photoelectrochemical cells. The first one is selection of effective photoelectrochemical cells materials. Difficulty in finding suitable semiconductors for water splitting and organic reforming. The second one is the need for specific physiochemical properties in materials. This to achieve the excellent photostability, to ensure high photoactivity in the visible light region, also to provide high electrical conductivity for efficient charge transport, and also to optimize the light absorption and mass transfer within the photoelectrochemical cells. The third one is design and scale up challenges for real applications. There is an ineffective light usage in practical photoelectrochemical devices, of potential issues that reduce the efficiency, and also the scaling up laboratory systems to industrially relevant size remains difficult. And the last one is the standardization and performance assessment issue. It needs a consistent criteria and benchmarking for comparing the photoelectrochemical cells performance.
There are few future developments of photoelectrochemical cells. Firstly is the development of more durable and long-lasting materials. Right now, there are many materials that may corrode and break down in water. Therefore, new materials that are more stable should be introduced in the future. For example, we can use metal oxynitrides as semiconductors to resist corrosion. Secondly, we can replace expensive catalysts in photoelectrochemical cells with cheaper materials. Currently, most of the photoelectrochemical cells use expensive materials like platinum and iridium oxide as the catalyst. Hence, we can replace these with cheaper catalysts to reduce manufacturing costs in the future. Thirdly, there is a potential to combine photoelectrochemical cells with normal solar panels in the future. The reason is because this could increase the efficiency. For example, in a hydrogen production plant, this combination is able to capture more sunlight, thus produce more hydrogen. Lastly, as we know nowadays, many industries and vehicles require large amounts of hydrogen as a source of renewable energy, and many more. Hence, photoelectrochemical cells can also be used in hydrogen production plants in a large scale in the future.
To conclude, a photoelectrochemical cell, or PEC, is a device that converts light energy, especially from the sunlight, into a chemical energy. This energy is usually stored as hydrogen fuel. The process is actually similar to photosynthesis in plants, where lights drive redox reaction. In PEC, sunlight helps to split water into hydrogen and oxygen. This makes PEC technology is a very environmentally friendly option for producing renewable energy. As the world becomes more modern, the energy demand increases. PEC research continues to grow. Improvement in material and efficiency show strong potential to overcome current limitation. In short, PEC play an important role for future energy system. They can provide clean hydrogen fuel while reducing carbon dioxide emission. This makes PEC a promising and sustainable technology for the future.